I'm delighted that we have Professor Shane Amara, neuroscientist, who will be speaking to us. Now, there will be many people who will have heard of him. There will be many people, I hope, will have read his book. Susan, this morning, showed it in praise of walking. I have both read it, I was saying to Shane, and reviewed it, so it's just as well I positively reviewed it, before I knew he was going to come and speak here. And it is absolutely wonderful. It really is a must-read for health professionals, social care professionals, politicians, transport people, of course, the environment. And I was interested because Andy Burnham started his talk this morning by saying how we have geared our lives entirely to the car. But that, of course, is a very recent phenomenon in the last 100 plus years or so. What Shane's book starts off with, which is absolutely fascinating and he will tell us more about, is actually in evolutionary terms, we are made for walking. It's how we've dominated the planet. Now, that may be a good or a bad thing, you might say, but nevertheless, we are built for walking. And not only that, but because of the depth of his expertise and knowledge, that actually he's been able to piece together and convey not just how good walking is for us, and we've heard that, but actually to understand some of the mechanisms that underlie that. Huge amount more. There are all sorts of enzymes and hormones of which I had never heard when I was a medical student many, many years ago. So an absolutely fascinating book, and I'm delighted that Professor Shane Amara, Professor of Experimental Brain Research at Trinity College, Dublin, will be speaking to us now. Please give him a warm welcome.
Are we mic'd up? Yes, great. So thank you for the invite to come here. I'm delighted to be able to do so. It's been a while since I've been in Manchester, and it's such a wonderful day. Cold, sunny days, I think I say in the book somewhere, are my favourite days for walking, and this is a cold, sunny day, and what a wonderful city to be able to walk in. Anyway, this is, as Jane has said, this is the book that I've written. I encourage you to go out and buy at least 10 or 20 copies each. Each copy is about 1/6 of a cup of coffee to me. So, anyway, on to slightly more serious things. So, what I want to do is start by picking on somebody who's a famous silly walker, and that's John Cleese. And above John Cleese is a quote from the great British anthropologist John Napier, who has been forgotten a little over recent years. And Napier says something interesting about walking. He's talking about walking in the context of primate evolution. And he says something that's 100% right and about half wrong, which is an interesting paradox, which I'll explore in the course of the talk. Human walking is a risky business. Without split-second timing, man would fall flat on his face. In fact, with each step he takes, he teeters on the edge of catastrophe. And that's kind of true, except it's not, because how many of you have fallen as you walk to your seats today? This is something that we're able to do, and we're able to do with great fluidity and grace. So I'm going to talk a little bit about how that happened. So it's very natural to think walking evolved on land. We're land dwellers, and of course we have a bias towards sturdy surfaces, and we have a slight bias against the sea. But it's not true to think that walking evolved on land. And we know this because of a whole series of genomic studies that have been conducted just in the last 2 to about 4 years. So this kind of, the developments that have been possible because of new genomic technologies have shed great light on the relationship between differing animal species. And I'm going to pick on one in particular here. All right, I'll show a few examples first. So if you look in the bottom of the ocean, you see this lovely little creature here, the rosy-lipped batfish, walks along the surface of the ocean floor. This fella, my favourite, the sea pig, transparent animal that walks along and eats waste of every type animal matter and all sorts of other things. And it walks very, very well. Now, if we take a different species, and hopefully, yes, there we go. What you're seeing here is a skate, and I'm sure some of you have eaten a skate at some point. This is a ventral view of the skate, in other words, a view from below, and it's on a transparent plexiglass floor, and it's lit from below. And if you noticed as it was moving around, it's got a set of legs. It has a set of hips. It's got a set of articulated muscles that allow it to push against the ground, and to do so with great ease, and it can swim very well. On the right here we have some mice. These are four-legged animals, formerly known as tetrapods, although they're quadrupeds as well because they walk on 4 feet. And the question is, these guys have hips, and they move and they push against the substrate to walk. And the question really is, does the gene complex that controls walking in the mouse, a land-dwelling, warm-blooded animal, share any resemblance at all to the gene complex that you find in this cold-blooded creature, which walks along the bottom of the ocean floor? They're separated in unimaginable amounts of time, about 420 million years by the counts that have been done with molecular clocks. And remarkably, maybe this will work. Maybe not. Oh, we're going to get to see him again, but anyway. And then the technology has died. So anyway, just to prove I know what's on my slides without looking at them, the genes that control the articulation of the body plan are known as Hox genes. And we mammals have them, bees have them, insects have them, and lots of other species have them. These control the articulation of the limbs during the course of development. And they go by a variety of different names, but basically HOX1 to HOX12. And if you look in the mouse, at the mouse genome, and ask what genes control the articulation of its hips and its legs, what you find is that a gene complex known as HOX9 control that articulation. Similarly, in the skate, you get exactly the same gene complex. So much so that you can flip them out of the skate and throw it into the developing mouse embryo, and the mouse develops entirely normally, and vice versa. We're back to life again. And if we move on one slide, please. I'm afraid to touch this. Okay, so here we go. So HOX67, HOX-C9, and HOX10. And if you want more of something, when you're building something genetically, the simplest trick is just to double it. And that's exactly what's happened in the case of the tetrapod in order to build the forelimbs, whereas the skate simply has hind limbs. Other than that, the genes are identical. Really, really quite remarkable. And you think about the aeons of time that separate these two species and the differing lifestyles that they occupy. So, it should be working, okay. Yes, there we go. So the conclusion I think that's reasonable, and it's one that's becoming more widespread, is that walking evolved in the ocean, and it evolved many hundreds of millions of years ago, long before animals made the transition to water margins and then onto the land. Now, if we jump forward a little bit in time, I'm sure this is Manchester. I'm sure a few of you have encountered the island next door. And down in the very southeast of this island, there's another island known as Valentia Island. And Valentia has one of the 4 tetrapod trackways that exist in the world. It's really quite something. This is a picture I took of it a few years ago. It was found by a Swiss geological student who was doing a survey in this area. And his calculations show that these tracks were made around about 380 million years ago. They've been astonishingly well preserved, and they're really quite something if you ever do go to get to visit Valentia. The creature itself looks something like this. It has an oddly shaped tail. It must have had a tail like that, because if you look at the ambulation, the track that it takes, it ambulates in an S-shaped fashion, and it needs a counterbalance, or else it would fall over. Its forelimbs are smaller than its hind limbs, and that's also clear from when you go and inspect the trackway itself. And it's open for public view. Okay, now getting up on our own 2 feet, so let's come right up to human development. How many of you here remember how you learned to walk? One person. Okay, I don't believe you. Okay, but that's reasonable. That's absolutely reasonable. I understand in that case. Yeah, you had a hippocampal formation developed at that point, whereas you didn't at 2.
No,
yeah. So, how do we learn to walk? If you look at the textbooks of child development, what you'll see are a series of milestones that a child is supposed to be able to walk or crawl at maybe 8 months or 7 months or whatever it happens to be. Should be able to sit upright at maybe 9 months unaided, and then should be making a transition at maybe 12 months, and a child should be more or less moving around at 15 months. How do we make these transitions? This is something that hasn't actually been studied terribly well, and it's a difficult thing to do. So what I want to do is focus on this paper by Karen Adolph. What she's done is something really, really interesting. It's to focus longitudinally on what happens in children to allow them to walk. You don't need to read the paper. The title tells you everything you need to know. You learn to walk by making thousands of steps and dozens of falls per day. Now, how do you do this? Well, what you do is you take a child to a walking laboratory. There's a gate mat. There are other surfaces for them to walk around on. And you track their position in three-dimensional space. And you literally count the number of steps they make, the number of falls they make, and you use this as a predictor for how well they'll learn to walk over time. And what's astonishing, and I think should be embarrassing for all of us adults, is that the amount of walking a child does is immense, around about 2,300 steps per hour on average. And they fall without injury, hence Napier not being quite correct, about 17 times an hour. Why? Because we're designed to fall back and sit as we fall. And this is, if you think about walking, it's a very, very peculiar transition that humans make. We're in a stable position on 4 limbs. It's hard to fall when you're crawling. It's much easier to fall when you're standing. And yet we make this obligate transition at around this period of time. More than this, children that don't fall much as they learn to walk faster. And the children who fall more tend to be slower in walking. But by about the age of 2 years, they all walk with approximately equal facility. Now, let's do something different, something that robots can't do. This is rough walking. This is from Mary Hayhoe's lab in the US. And what you have here is somebody wearing a mobile laboratory. So you can track eye gaze, you can track limb position, and as he swings around here, you'll see he's got a PC or a laptop on his back. And humans are very good at this. With a little bit of training, you can jog and run on surfaces like this, and you can do this very, very safely. And really, really quite remarkable. And the question is, how do we do it? So as you'll see, he'll arrive and he'll come to the terminal position where this mat is. And there he's at the end. So the question is, how do you do this? Well, again, modern technology allows us to understand how it is that humans can walk on surfaces like this. And this is how you do it. You look ahead by about 2 meters and you flick your eye back. And the dwell time that your eye spends on the place that you're looking at predicts where you're going to put your foot. So you make the decision in about 1/5 of a second as you're moving forward, while your body is tilted to walk in this position. And those of you who do lots of regular hiking will know that you've done this many, many times. And generally you don't do it without injury unless the ground is deceptive in some way and you end up stepping into a sinkhole. So this is again, when you think of the speeds that are involved here, to make these decisions in fractions of a second and to keep moving at what is in fact quite a high rate is really quite remarkable, and it shows you how well adapted we are to engaging and walking in different surfaces. One thing I just want to point out, if you look at the angle of the head, one of the things that the brain does is stabilize the position of the head while you're walking. And it stabilizes a line between the corner of the eye and the auditory canal. What it attempts to do always is to keep that line parallel. So if you find you slip on a slippy surface, the first thing that happens is your head drops and your brain is trying to keep you in that position. So your body is guided from your head. It's not guided from your feet. Now, I'm sure most of you, all of you who are walkers, realize that walking makes you feel good. It's one of the reasons for doing it. And there are all sorts of reasons to think that it might make you feel good, and it's something that we should do more of. What I want to do is just focus briefly on a small study and then on a large-scale study, showing how walking can change how you feel, and in particular how walking can be, in some sense, a prophylactic against major depressive disorder. So if you unpack the title here for a moment, walking facilitates positive affect. That's psychologists speak for feeling better. But here's the good bit, even when you expect the opposite. So in this study, what they did, it's in Iowa State University, they had enrolled students in a study, and they were split randomly into two groups. One whose job was to sit in a room and judge pictures of buildings around the university, and the other was to go and actually look at those the physical buildings and judge the aesthetic quality of them. And they got them to fill in some questionnaires about lifestyle, including how much walking they do and whether they like walking or not. And then they got them to do these tasks and then judged how they felt. And this is what they found, that people who did the incidental walking rated their own mood as being dramatically different and better after having done the walk compared to the group that just simply sat in the lab. And more than that, the group that, quote, dread walking, the group that dislike walking, unexpectedly find their mood improves even more. So engaging in some degree of physical activity where you have to walk around, even though you're instructed to do so by somebody else, even though you don't want to do it, will actually make you feel a bit better. Now, these are, of course, small-scale studies. Happily, we're in an era of big data, and we can grab data on all sorts of things to do with mood and ambulation and all the rest of it, which we couldn't do even 10 years ago. So here's a very important study from Australia. This is of a very large cohort, about 34,000 adults. There's been a more recent version of this, which was just published with 1.2 million adults, but I got the same results, but I won't talk about it. What they did was track people for 11 years and look at the likelihood that they were going to succumb to major depressive disorder, and then looked at the likelihood of succumbing to major depressive disorder depending on how much you walk. And what they found was that the likelihood of succumbing to major depressive disorder fell by about 12% in the groups that were walking compared to the groups that did not walk. So the most active versus the most sedentary. So this is an effect which is really quite large. In many of the studies, the commentaries on this, the effect size is about the same as you get for cognitive behavior therapy and about the same as you get for the best drug treatment that we have available for major depressive disorder. Now, this is prophylactic, it's not a cure, so this is ahead of time. We don't know anything yet about the effects of depression, of walking on people who are already depressed. So I caveat that when I say that. Now, will walking make you creative? Lots of people, if you read autobiographies of philosophers and artists and others, you find that walking is a core component of their lives. Bertrand Russell, the great philosopher, used to go for an hour's walk prior to writing, and he always, or his friends jealously used to say that he would be able to write for the morning without making a mistake. Stephen King, the novelist, does the same, and many, many others do this. But this is curiously a question that hasn't been investigated until recent years in any formal sense. So a way of testing creativity is to ask people to generate uses for common household objects. So you bring them to a lab and you hand them a can of beans, a pen, a paper clip, a whole series of other objects, and you say to them, come up with as many uses for each of those as you can in a minute. And some people are very good at this, some people are very bad at this, and you see a great variation among individuals. Now, what they did in this study was get people to sit in the lab for 10 minutes before doing this test of divergent thinking, as it's called, or they brought them for a walk for 10 minutes before doing this test of divergent thinking. Now, the walk is literally just a stroll. And what you find is that about twice as many ideas are generated by the people who walk compared to the people who are seated. And in lots of clever variations, they tested them on treadmills, they had them seated on treadmills, they did all sorts of other things. And the movement is the thing. The movement really, really makes a big difference. And similarly, we don't need to worry about the detail of it here, but they also got them to develop and generate novel analogies regarding things. And again, the walking group came up with more diverse and interesting walking analogies. I hesitated before doing this slide. I hope it's okay. Not all walking ideas are good ones. Sorry. I guess it's okay. Anyway, there you go. Okay, so how much do you walk? Well, we now know a lot about how much the average adult walks. And the answer is that we don't walk very much. So formerly we were stuck with self-reports, and people just don't know. If I asked anybody here randomly how many steps you took last Thursday fortnight, you'll guess, and it'll be wrong. And all of the self-report data in this area just are rubbish. You just should throw them out. But now, because of smartphones, we can actually grab data that are much, much more reliable. So here's a remarkable study by Tim Ailtoff and his colleagues from a couple of years ago. And what they did was explore walking in about 700,000 people over 68 million days of walking across all of the countries that you can see lit up in these various colours. And what you see is a really marked variation across differing regions in the amount of walking that people do, with the Japanese walking most at around about 5,500 to 6,000 steps per day on average. A child does that every 2 hours or 2.5 hours. Okay, so it's not much at all. And here in Western Europe, we're more like 4,500 steps a day. It's really not very much at all. And Saudi Arabia, they walk the least, and that appears to be attributable not to the heat, but to the simple lack of provision for walkers, because of course this part of the world has had nomadic tribes for thousands of years, but the cities do not have footpaths. So how we design our cities is really, really important. And we can engage in much more walking if our cities are designed to allow us to walk. Can I prove that contention? Well, I can. So you can get an index of walkability. If you go online, you can discover one for the US, and you find all sorts of interesting things out. Highly walkable cities are much more expensive, but also you can look at the patterns of activity in those cities. So cities like New York, people walk an awful lot, and cities like Atlanta, people hardly walk at all. And there are great differences. So if you look at a highly walkable city, this is Boston, San Francisco, New York, you can see a huge peak in the morning, a big peak at lunchtime, and then a very long tail in the evening. So people just walk a lot more. And in the low walkability cities, you see a much lower level of walking. And at weekends, you see a really nice long tail of activity in walkable cities versus cities that are difficult to walk in. So the design of our urban environment has a dramatic effect on how much walking we're capable of doing. Now, how many senses do you have? If you did biology in school, you were told 5, maybe. And these are the ones that we're usually told about. The answer is probably closer to 11. And there are senses that we tend not to be aware of. So I'm going to ask you to do a little experiment on yourselves. Can you put your hand out in front of you, your right hand or left hand, it doesn't matter, and just look at your fingers, okay? Now, sweep them from side to side while looking at them. They should blur, yes? Yeah? Now, look at your fingers again, and shake your head from side to side. Do they blur? No. Ah, amazing. This is because the head stabilizes inputs to the retina, which are to the visual system, and subtracts movement from the direct inputs it receives. This is technically known as motor efference copy, but it's the thing that allows you to make inferences without thinking about it, about the nature of the world that you're walking in, to generate maps of your world and to have a positional sense. Now, we can ask this question, which sense is most important for getting around in the world? And the one we humans usually say is vision. That feels right. We look around the world, we can see where we want to walk, and we can walk to it. But is that actually correct? Well, we can address this question in a particular way. We can take people who are blind from birth, people who became blind later in life, and people who have normal vision, and ask them to do wayfinding tasks. So there are tasks known as triangulation tasks, where they start at an origin, walk to a certain point, go to another point, and then they have to find their way back to that origin. And what you find is, irrespective of whether you can see, so you've got normal vision now, obviously you're blindfolded when you're doing this, you've become blind later in life, or you're blind from birth, performance is approximately the same. What they say, and this has been very often observed, results provide little indication that spatial competence depends on prior visual experience. It's movement in the world that is the thing, and we build up our map of the world through all our senses and not just our visual sense. So we shouldn't assume that cognitive mapping capabilities are lost merely because you don't have good vision. Now, talking about getting older for a moment. Everywhere we look, people are getting older. This is a wonderful graphic showing that from 1960 until 2015, you can see average life expectancy has risen everywhere. Across the world, it's about 72. In Japan, it's about 88, or 86, I think. The trajectory has been up. This also means that our planet is aging. And we need to think about how people can age in a more healthy fashion. And there are lots of things that we can do. But what I want to do is just focus on this top one, which is to talk about movement for a moment. There's quite a bit of evidence now, and I think it's very well founded from various places across the world, showing that placing aerobic exercise in particular at the core of the prescription for healthy aging is possibly one of the most effective things we can do to assist people to age well. Making sure exercise is something that people do and do regularly is something that doesn't happen often enough. I saw a study, for example, in this country that showed that GPs talk to patients about exercise on less than 20% of occasions. It's not something that is really put at the center of healthcare in the way that it could be. Now, why should we do it? Well, there are all sorts of reasons, but one of the important reasons is that aerobic exercise maintains the plasticity of the brain right throughout life. So this is a study by Art Kramer and his group in Chicago. And what they did was very simple. They took a group of 120 older adults in their late 60s and early 70s, divided them into two groups, a sedentary group who just continued living life as normal, and a group that were brought out for a 1.5 mile walk 3 times a week over the course of a year. And they measured the volume of this structure, the hippocampal formation, or the hippocampus. This is the structure that's attacked first by Alzheimer's disease, and damage to the hippocampus results in a dense amnesia, and one from which you will not recover. What they showed was that aerobic exercise causes an increase in the volume of the hippocampus over the course of the year of this study. So getting out and moving has a profound effect on the fabric of the brain. More than this, though, what they showed was that the age norm memory performance in the active group, the walking group, actually got better compared to the sedentary group. So much so that the 72-year-olds performed much more like 70-year-olds. What they did in essence was reverse the functional aging of the brain. And then there are all sorts of other things like this wonderful molecule, brain-derived neurotrophic factor, goes up measurably in their circulation. Now, I've said already that lots of people are getting older. One of the other things we're doing is we're living urban lives now. And a majority of the population now live in towns and cities rather than live in the countryside. Something that happened just only 3 years ago. It's a really new departure in our existence on this planet. And if we look at our towns and cities, one of the things that is obvious is that most walking will be in towns and cities. So we really need to think about how we design our towns and cities to facilitate walking. This is just a truism. Our cities used to be terrible for walkers. This is a poem by John Gay from the 1700s describing London and the phenomenon of having chamber pots emptied over your head as you walk about. And in Georgian buildings, you often see boot scrapers at the entrances to doors, so you could scrape the stuff off your feet. Now, but think about what we've done where human waste handling is concerned over the last 100 years. Who gets typhoid anymore? Nobody. We've made this a public health priority, and we've designed our plumbing systems and other systems to ensure that contamination of humans by waste products is brought to a minimum. But we haven't done this for other aspects of public health is concerned, and in particular where movement is concerned. So I think our streets are still often terrible for walkers. Here's an important study by Laura Asher, conducted here in the UK just a couple of years ago. And what they did, very simple, is to ask the question, can older pedestrians, people in their 70s and 80s, can they cross the road on time? When they push the beg button to get across the road, do they have sufficient time to get across the road? And the answer is no. In this sample, 85% or 84% of males and 94% of females were unable to walk across the road with sufficient speed. Why? Because the road crossing is designed for a young, healthy adult in their early 20s who can walk at least 1.2 meters per second. But if you're older, if you're infirm, if you're in a wheelchair, if you're using a walking stick or whatever it happens to be, this is going to be much, much more difficult for you. And then there are other issues to do with the design of pedestrian crosswalks. Are they lowered? Is the road brought up to the same level? All of those kinds of things. These are not problems that can be solved by individuals. These are problems that depend on the policy that councils adopt where walking is concerned. Anybody recognise this place? I'd be very pleased if you did. This is Galway, where I'm from, on the west coast of Ireland. I bring this up for a reason. Galway is built on a river that divides the town in multiple ways. And if you drive in on the motorway from the west, this is what you meet. A redesigned motorway where no pedestrian walkways were put in place. So on this test, it took 14 minutes to get from here to there, because cars are more important than people. The shops are over here, and residential areas are over there. Now, imagine you're an old person struggling with bags, having done the shopping. You're going to be imprisoned in your home. Imagine you have another walking impairment. And if you look around, you'll find places like this all over Europe, all over North America, and lots of other places you go where pedestrian movement is relegated to a second or third thought, and it's certainly not the concern of the road traffic engineer. Now, this is Taormina, one of my favorite places in the world, in Sicily. And if you go to many of the Italian towns and cities, you see this wonderful phenomenon in the evening, the passeggiata, where people come out to walk and talk and look at each other and all of those kinds of things, eat ice cream perhaps, or a gelato. And I think what we need to do is think much more about designing our towns along the kind of principles that are in many of these towns and cities. And I'm using this acronym EASE, that our towns and cities need to be easy to walk. They need to be accessible to all. That means everybody. It means people in wheelchairs. It means people on crutches. It means people with visual impairments and all of the other things. These need to be placed at the core of it. And our cities and towns need to be safe, and they need to be enjoyable for all. So that means taking cars out wherever possible, which is not a comfortable thought. But as Jane said at the start, cars are around for about 100 years. Will they be around for another 100? I don't know. Now, I'm going to finish up and ask this question. Why do you have a brain? It's a strange question to ask, but it's not a stupid one. If we can rephrase it, what problem does having a brain solve for you? It's another way of thinking about it. Well, if you look at this creature here, this is a sea squirt, a beautiful creature, I think. You can see it's got a vascular system. It sucks water in and expels it and does all sorts of interesting things, but it doesn't move. Now, if you look at the sea squirt in its early life, it has a spinal cord as a larva, so it's in the same phylum as we humans, phylum Chordata. It has a very small brain. It has a primitive visual system. If you look at it in cross-section, you can see that it even has a mouth. It's got a vestibular system to tell it which way is up and which way is down. And as it gets older, one of the things it does is transition from a motile life to a sessile life. In other words, it stops moving and it sticks itself to a rock. And the first thing it does is ingest its own nervous system. And I think there's an important lesson there. So I ask you to imagine what it's like to be a little sea squirty and what effect it has on you. Well, we know the answer. It's not good. If you take healthy young athletic males in their late 20s and you put them in this waterbed which supports them reduces the effect of gravity so they don't have any strain on any of their joints. You do this for 3 days. They only get out for toilet breaks. What happens? Well, what happens is remarkable. The muscle volume in the thigh goes down measurably by about 10%. Muscle strength goes down by a similar amount. And muscle viscoelasticity, so this is the property of muscle to be deformed and then reassume its previous shape, also falls in these healthy young adults. And one of the things that has become clear just again in the last couple of years is that molecules derived from the activity of muscle, known as myokines, circulate freely when muscle is under strain. So it must be active, pass into the brain and have all sorts of interesting effects in terms of brain integrity and brain resilience. That's a very obvious conclusion that being Homer is bad for you. Okay, I will stop there. Thank you very much.
Yes, we're going to